Hello everyone, welcome back to a new type of video where I am going to be teaching you the fundamentals of circuit design. And this circuit design not only applies to Minecraft, but real life as well. So whether you are just looking to improve your redstone skills, or actually interested in becoming an engineer of some sort, I think you'll find this series enjoyable. Okay, so every circuit has at least one input, which in this case we are going to call A, and at least one output, which we are going to call Y. Now, when something is on, we call it high, and it's represented by a 1 in Boolean algebra, and we're going to get more into Boolean algebra later, but just keep that in your mind. When something is on, it equals 1, and when something is low or off, it is denoted as a 0 in Boolean algebra. So in this circuit, we have our input, which is a lever or a switch, some wire, and our output, which is an LED. And the relationship to this input and the output is that A equals Y. If A is 1, Y is 1. If A is 0, Y is 0. So hopefully that all made sense, because now we are going to look at our first type of gates. Now gates are defined as having at least one input and changing that input in some kind of way into a new type of output, and you'll see what I mean in a second. So this is the most basic kind of gate. It's called a NOT gate, and in actual circuit designs, you'll see it like this. It's a triangle with a little circle on the end. The kind of flat end of the triangle is the input side, and the side with the circle on the end is the output side. So how it works is it just inverts the signal. So right now, A is 0, and Y is 1. Now A is 1, and Y is 0. And we denote inverting as an apostrophe in Boolean algebra, as you can see here. So Y equals A apostrophe, or A inverse, or A naught. You'll hear people use those terms interchangeably. Whenever there's a NOT gate, it can be Y equals A naught, Y equals A inverse, and it's just written with an apostrophe. Okay, so next, what happens when we combine two NOT gates? What does the inverse of an inverse equal? Well, if you know some basic math, you'll know that if you take the inverse of any number twice, it just becomes itself again. And the same is true in Boolean algebra and circuits. So, as you can see here, we have two NOT gates, one here, one here. And the input A is equal to the output Y. You can see Y equals A naught naught, which is just A. And if we make input A equal 1, output Y equals 1. If input A equals 0, output Y equals 0. So essentially, the circuit is just exactly what we had at the very beginning over there. The input directly correlates to the output. Up next, we have the OR gate, and the OR gate is defined by having any number of inputs, and as long as at least one of those inputs is high, then the output will be high. So as you can see here, we have two inputs, A and B, and one output, Y, and as long as at least one of these is high, then the output will be high. So if B is high, output is high. If A and B are both high, output is high. If just A is high, output is high. And if A and B are both low, output is low. And OR gates are denoted by a plus sign in Boolean algebra. So here we have Y equals A plus B. If we had a third input called C, it would be Y equals A plus B plus C. Next, we have the NOR gate, and the NOR gate is completely identical to the OR gate, except that the final output of it is inverted. So it is essentially a OR gate with a NOT gate at the end. And what you're going to notice with the schematic of the NOR gate is that it is exactly the same as the OR gate, except with that little circle at the end. So anytime you see that little circle at the end of any kind of gate, you can assume that the output is inverted. So let's see it in action. We can see that both of our inputs are currently low and the output is high. But as long as any of these inputs are high, the output will be low. So B is high, output is low. A is high, output is low. A is high, B is low, output is low. A is low, B is low, output is high. Up next, we have the AND gate, and the AND gate is defined by having any number of inputs, just like the OR gate, but every single input needs to be high in order for the output to be high. So in this scenario, A is low, B is low, so Y is low. A is high, B is low, Y is low. A is high, B is high, Y is high. A is low, B is high, Y is low. And the notation for the AND gate is just multiplication. So over here we have Y equals AB, so Y equals A times B. And of course, just like with the OR gate, if we had 3 inputs, so A, B, and C, it would be Y equals A, B, C. Up next, we have the NAND gate, and just like the NOR gate, the NAND gate is literally just an AND gate, but with the final output inverted. So every single output needs to be high in order for the output to be low. So A is low, B is low, Y is high. A is high, B is low, Y is high. A is high, B is high, Y is low. A is low, B is high, Y is high. Next, we have the XOR gate, which is defined by needing an odd number of high inputs to get a high output. So as you can see now, A is low, B is low, Y is low. Now A is low, B is high, Y is high. A is high, B is high, Y is low. A is high, B is low, Y is high. And it is denoted with a little, it's a bit hard to see, but a plus sign with a circle around it. So A XOR B, and of course if we had a third input, it would be A XOR B XOR C. And as you would expect, the XOR gate, just like the previous gates, also has an inverted version called the XNOR gate. And again, exactly as you'd expect, is just an XOR gate with the final output being inverted. So A is low, B is low, Y is high. A is high, B is low, Y is low. A is high, B is high, Y is high. A is low, B is high, Y is low. Okay, so this is where things really start to get interesting. What I have before you is an XOR gate that is made completely out of NAND gates. So like the XOR, it has 2 inputs, A and B, and 1 output, Y. And it is made solely from NAND gates. So here's a NAND gate, these two blocks are NAND gates, another NAND gate, NAND gate, NAND gate, and the output of that NAND gate is our final output, which goes to the LED. And this is what the circuit looks like from above. And we can see it in action, exactly like a normal XOR. And this same exact thing can be accomplished using NOR gates, which we can see here. So NOR gate, NOR gate, NOR gate, final output goes to the LED. And again, exactly like a normal XOR. And this is what is called universal gates. So NAND gates and NOR gates can be used to make any of the previous gates that you have seen. So just know that as long as you have NAND gates or NOR gates, you can make literally any other type of gate. So to cap off this episode, I want to make a very quick introduction to Boolean algebra. So as you can see here, we have our 4 inputs, A, B, and C. And we can just directly look at where those inputs go. So A goes to here, which is an AND gate. And B also goes to the same AND gate. So we can say that A and B are being ANDed, A times B, as we discussed earlier. And the output of that is going to this OR gate. So what are the inputs to this OR gate? This OR gate has input C and input D going into it. So we say A and B, or C, or D. And this helps us to see what the final output is. So output Y equals A and B, or C, plus D. And this essentially allows us to easily test what the final output of the circuit will be based on the inputs. So you can sub in random numbers for A, B, and C, and it will give you what the final output is. For example, if A is 0, B is 0, C is 0, D is 0, we will get 0 ANDed with 0, which is 0, plus 0, ORed with 0, which again is 0, ORed with 0, which is 0. And as you can see here, that is exactly what our final output is, 0. Now let's pretend that A is 1. So if A is 1, or A is 1, everything else is 0. So 1 ANDed with 0 is 0, as we saw. ORed with 0, again 0, ORed with 0 again, 0. So when I push A to be 1, the output should still be 0. So let's try that. So A is 1, output is 0. Let's try one more example here. We're going to make A1, B1, and C and D both be 0. So we're going to say 1 ANDed with 1 is 1. ORed with 0 is still 1. ORed with 0 is still 1. So by that logic, the output when A and B are 1 should be 1. So let's try that. So A is 1, B is 1, output is 1. So this is why Boolean algebra is very useful, because you can simply design the circuit on paper without having to actually build it and test all the outputs on paper. And as we'll see in some later episodes, it can be used to massively simplify circuits and get rid of a bunch of gates that are unnecessary and will just cost you extra resources. But yeah, that is going to do it for this episode. I hope you found it helpful. I hope you enjoyed it, and I will see you in the next one.